state, then V in the stationary state is, you bring in the left hand side here, I get minus E times electric field and tau over M, right? Right? This is something that you'll find in Cadell, in Ashcroft and Mermin, everywhere. So you get the stationary state velocity. With the stationary state velocity, you can define a stationary state current. This is from charge conservation that you find that the stationary state current then, how do you define the stationary state current? You define it as minus n, which is the number density of electrons, times their charge, times the V stationary state. You plug it in together for the value of V here, the signs cancel, you get n squared E tau over n, right? This is a J stationary state. And this is just one more step to get to the Drude conductivity, because Ohm's law tells you that J stationary state is defined to be also equal to sigma times the electric field. Okay, so the electric field will cancel from both sides, and you get sigma equal to N squared tau over M. This is Mr. Drude. Okay, so the conductivity that you would measure would have to ensure in the laboratory that you have waited long enough so that all transient effects have died down, and you get a stationary state value, and that's the Drude conductivity. Okay? So now, and of course, you can also measure frequency-dependent conductivity by, instead of applying a static battery voltage, you can apply an oscillatory voltage, and then again you can look at the static, non-transient stationary state conductivity, and that will be omega dependent. We are doing the same thing here in the tight binding model. Nothing more fancy than that. I have electrons hopping from side to side, and they create a current, okay, like the Drude current. And then you claim that in the stationary state, right, your nk dot must be equal to 0, right? That is, as many electrons will be leaving a site as electrons flowing into that site in the stationary state. So in the stationary state, there is no net bond current. That is, if I have, okay, I'll do that later on, that the current of particles leaving a site will be compensated by current of particles going into that site in the stationary state. But the controller will know that if you stick in an ammeter between two sides, you will still measure a current. And that is the bond current, sometimes also called the persistent current. Okay, it's a counterintuitive thing, because normally you say that you see a net current only when you have a superconductor. For a normal state, you don't see a net current because of scattering events. But due to the Aharonov-Bohm flux, you can actually see a net current. And it has been seen experimentally. We'll discuss that a little bit. Yeah?
That's like a ground state current. You don't expect currents in ground state?
The HK, the H matrix element that we calculated was the ground state. Right. Okay? So this is quite fascinating stuff, actually, that you see this card. Now, there's a simple geometry where I would ask you again to do this as an exercise, that suppose now I simplify my tight binding model.
So,
X minutes, I can draw it. So I have a closed ring, and you have a finite number of sides. In particular, to be very simple, I'll construct a 3-side ring. So it's a tight binding model. You have side energies. You can have hopping, 1 to 2, from 2 to 3, from 3 to 1, and vice versa. And we'll see how we can implement whatever we have done here in terms of this model. Here, somebody had a question. Yeah.
so plus 160.
With only 3 sides. Experimenters will tell you how to create those things in the laboratory, which I'm not very sure of. And so what is the tight binding Hamiltonian? I'll further assume that all these three sites are symmetric, so that my epsilon 1 is the same as epsilon 2 is the same as epsilon 3, call it epsilon. So if I have only epsilon, then the first term, epsilon comes out, and I simply have this. And you know that from closure property, this is just the unit operator, right? The first term. But now I have the other terms, and so I have juggle with this. J. So I'm assuming also, sorry, T. I'm also assuming that T12 is the same as T23 is the same as T31. Yeah. So it's the same as T. So I get a minus T. However, there's the RNR bomb phase. So you have projection operators 1 plus 2, 2, 3 plus 3, 1 times RNR bomb phase e to the minus I5. Constant phase because I have assumed these sites to be all equivalent, plus of course the Hermitian adjunct. You understand what I'm doing? I simply have a three-site problem. I'm assuming the three sites are symmetric, so all the site energies are identical, okay? And the hopping terms are also the same, so I have only one T. And the phase factors are also the same because the sites are all equivalent. All right? So this is my simple-minded Hamiltonian. And you can actually easily write down the 3 by 3 matrix for this Hamiltonian. And this is an exercise for graduate students. That the Hamiltonian, then of course in the site representation as a 3 by 3 structure, it has got a J, and it's a 3 by 3 matrix, only with off-diagonal terms, because the site energy I can eliminate because it's a constant term. I can redefine my zero of energy, e to the I5, e to the I5, 0, e to the power minus I5, e to the power minus I5, e to the I5, 0. So that's your 3 by 3 Hamiltonian, right? Matrix. Clear? The basis that we have chosen is the site basis, 1, 2, 3. So you can just simply read out that this term is not there because I have subtracted that term or added that term. And so now between 1 and 2, the non-zero matrix elements will come and be multiplied by that factor e to the minus I. And so on, right? So, you know, this is beyond 2 by 2, this is the simplest 3 by 3 that you can work out. You can calculate the energy eigenvalues. You'll find three different eigenvalues for a 3 by 3 matrix. You can also calculate the eigenfunctions. This I leave it as an exercise. And having done that, then you calculate the bond current between, let's say, the site 1 and 2. What did we say? That I12 in the stationary state must also be the same as the current going in the other direction. And I12 must also be the same as I23 in the stationary state, because that means that as many electrons will be visiting that state 2 as leaving that state, and so the net bond current will be 0. But as I said, if you stick in an ammeter, you will measure it. And let me now give you the final answer. And please do this exercise. It's a nice exercise, and this has been experimentally seen, and you will see the reference in, let's say, a book by Joe Emery on mesoscopic systems, experiments done in the IBM labs in the mid-80s, as sign of this flux. So please do this as an exercise. Now, this is a very fascinating thing. What we are saying now is that between two sites, I stick in an ammeter, and I will see a current, an electric current in the ground state. Which electric current, of course, apart from this fundamental constants, of course, will depend on the this is T, right? The hopping parameter as sign of the total flux, right? So now, flux depends linearly on the magnetic field. Okay? Yesterday I said that if you change the sense of time t to minus t, you must also flip the direction of the magnetic field. So, current, of course, would flip the magnetic field. You keep on tuning the magnetic field. You see the oscillation. These pictures are there in Emery's book. If you change the direction of the B field, the current is reversed. Okay? So this is the current that you are seeing, an electron going in a mesoscopic ring, threaded by an iron or bomb flux, and in the stationary state, in the ground state, you see a current. Okay? Now, where is the second title of my lecture coming in? Is that, you see, we have used only quantum mechanics. Okay? We have used only quantum mechanics here. Quantum mechanics says that the Schrödinger wave function, which has got a phase, and therefore it has, between two different paths of the electron, we have a definite phase relationship. That is called coherence. And it is this coherence which is responsible for Young's double-slit experiment interference pattern, even in optics. Remember, you have to have a coherent source, they say, in order to see interference effects. So it's the underlying coherence. So presence of a persistent current in the ground state between two sides in a mesoscopic ring is a manifestation of a quantum coherent phenomenon. All right? And what we have done, and we're not going to, I'm reluctant to talk about research problems here of mine, that is that with my Israeli collaboration, that if you put noise in this system, you can actually see how this current gets decohered, and the current will try to decay to zero. And if the current survives, and this is what we did in the context of a qubit, which we'll discuss a little bit, that you can in fact capture, you can maintain partial coherence even if there's presence of noise. I don't have time to discuss these noisy effects here, except I'll allude to it the next 15-20 minutes of my allotted time. So this is something, but this is an exercise, not the noisy effects are actually non-trivial, but when you, for this 3x3 problem, all of you, I mean the students, because I think the faculty have many other things to do, they will not do this exercise anymore, that you can actually calculate the energy eigenvalues, energy eigenfunctions, put them in that formula that I have given you, and calculate what is the bond current. Okay? So this is the claim, right? Now, what Das is saying, they are all important things. If you have multi-electron problem, how do you fix the number of electrons with the chemical potential bath, etc. These are all important questions, higher level questions. I'm saying a simple quantum mechanics or a tight binding model with a magnetic field for a three-side problem allows you to do this. Okay? So I'll just quickly summarize what I wanted to do in the next half, which is that basically this physics of two-level systems. Let me just get rid of this one. So you have this R1 vector, R2 vector, and R3 vector. So you have three equilateral, three isosceles triangles comprising this one single equilateral triangle. So between sides 1 and 2, we are worried about this triangle. And calculate the flux to that triangle. Is it clear?
So when you were incorporating this hopping term T, basically the electrons is moving from one side to another.
Yeah.
So it might not enclose the path. It
This
might
is precisely what the Aharonov-Bohm effect is here. It is what say that you may not have the magnetic fields and the electron field, the paths cross each other, yet you see the effect. That's what I labored on in the morning. See, you may not have a magnetic field, but you have vector potential here. And that's what is responsible for this. That's what we did in the morning.
The difference between
I think we should discuss it outside because you're wasting our time vis-a-vis the other. I don't understand the question because in the morning we kept on saying that even if the electrons go in regions where there is no physical magnetic fields, because of the vector potential, you have a net phase shift. And that's what gives rise to the interference effects. Already, simple two-state systems have cropped up in much of our discussions. And if you understand the physics of two-state systems, well, at least as far as I am concerned, I have to understand the simplest thing first. You have actually understood a lot of things. Where do two-state systems occur? They abound in chemistry and in physics. And your examples will give you, for instance, any spin half problem. You see that in ESR, in MR, neutron scattering. Etc. Then we saw already when we do a linear combination of atomic orbitals, you have this bonding and anti-bonding states. Right? So this is the basis of Pauling's work on the nature of the chemical bond. Then I also mentioned in the passing, though to discuss it, this is the stuff that we did a lot of work together, work in the mid-80s, where you have hydrogen in niobium, and people have done neutron scattering experiment, where you have the realizations of two-state systems again. So you have defect states. For example, hydrogen in niobium. Then next week, we're going to talk about Dirac points in graphene. Qubits in quantum information. Now you might think that this is physics, this is only chemistry, this is also physics. But then this very important idea of chemistry is called hybridization of states, which abound in the carbon-based materials, which we'll discuss a little bit more again in the context of graphene. You see this spin half two-state problems. So I think I'm almost coming to the end of this. Say things in words. So let me go back to this double oscillator problem. So what did we say here? We'll say it slowly again. That when you have the two oscillators far apart, you have a single harmonic oscillator problem. For single harmonic oscillator, the wave functions, the ground state wave function is a symmetric wave function. This is the first excited state wave function. When you try to bring these two wells closer and closer, you start having overlap. And then the meaning of overlap is this, that so if I now go to the infinite distance A, I have two independent harmonic oscillators, each having this ground state and the first excited state. I try to bring these two oscillators together, the Merz-Bachar problem, and you are somewhere here, you have a tunnel splitting, which means that you are now working on the linear combination of psi 0 and psi 1, They are like the bonding and anti-bonding states. The bonding states have lower energy, that's why they're called bonding. In terms of the atomic orbitals in hydrogen-like atoms, it's the effective Coulomb energy that gives you this bonding states. And so that's the physics, right? That is what you have here. And so now what experimental is there? So it's, for instance, as I said, like if you take niobium, it's a body-centered cubic structure. Niobium is superconducting at low temperature, below something like 10 Kelvin. What is it, 10? 8.9. 8.9. So, but you can kill superconductivity by doing the Meissner effect, by having an external magnetic field. So it's still normal state niobium that the experiments were carried out. And you put in very low ppm level hydrogen into it. You also have other impurities like carbon, oxygen, etc. They occupy the tetrahedral sites, and they are being heavier. They actually don't move as much as the hydrogen does. Why does the hydrogen move? We discussed it. The electron is post-quantum mechanical because its mass is small. Remember, the de Broglie wavelength lambda has an h divided by the momentum. So mass occurs in the denominator. So the lighter the particle is, you have a more extended wave function. So hydrogen, the first thing in the periodic table, also is only a proton as it goes inside the material, and it still has a substantial de Broglie wavelength. So therefore it is quantum mechanical, as opposed to, let's say, carbon or nitrogen impurities, which are much heavier, they are localized. But to see these effects, you have to go to very low temperature. So what you do is, you go to a reactor and you shove in a beam of neutrons and on the sample. What the neutron feels is that neutron has nuclear interaction. We're ignoring spin now. There's no proton spin in the problem. Neutron spin is also ignored. You're not looking at spin scattering, but you're looking at nuclear scattering. So the neutron comes and gets scattered. The scattered neutron carries with it the phase information of the hydrogen atom. The hydrogen atom phase will depend on the physical location of the hydrogen. But the hydrogen can be either here or there because it keeps on going like a quantum clock, like a tunneling thing. So the hydrogen is actually moving, and the neutron then catches the hydrogen in its flight, and the scattered neutron will give you the information to what is called the wave vector frequency dependent structure factor. Okay? So the neutron comes in and gets scattered, and you look at the what is called the structure factor, the scattering cross section. So there is S of Q, Q and omega. So Q is like a wave vector, so you can probe the length scale over a magnitude of Q, or you can probe the time scale phenomena by looking at time scale of the order of 1 over the frequency of the neutron beam. Basically, these are determined by the average time the neutron spends in the scattering process. This is one experiment. There are several like proton magnetic resonance experiments you can do also, or the ammonia laser problem, where you see this two-level system. So where is decoherence coming in here? So this quantum tunneling is a completely quantum coherent phenomenon, exactly as the average bond current in the ground state is a quantum coherent phenomenon. It has to do with the coherence of the quantum phase. All right. Now, as I said, when you dissolve hydrogen in a metal like niobium, hydrogen goes like proton. Proton has a positive charge. The metal has a bunch of conduction electrons. So there's a strong coupling between the proton, the electrostatic Coulomb interaction. This becomes dynamical because everything is moving, and you have this coupling. Therefore, the bath, if you like to call it, external system, is like a fermionic bath. That's a matter of detail. But what happens is, as the hydrogen tunnels, it drags this quantum bath of electrons along with it. So you have what is called quantum friction. And so this scattering process, I'm saying it in words, I'm not going to discuss these things in detail. The scattering process, therefore, looks at a process which is not completely quantum coherent. So how What are the experimental signatures of this tunneling effect?